This is Professor Stephen Sekula from Southern Methodist University, and this is part two of a two-part lecture called The Movement of Electric Charge. Now in part one, we investigated the motion of an electric charge, a single charge in a uniform electric field, and we came up with a relationship between how the charge moves and what the electric force field is doing to it, how it's acting on it. We then considered the case of two charges in the form of a dipole, and we saw that a dipole that starts out with its dipole moment oriented at an angle to an electric field will be forced to rotate by the electric field around the center of the dipole. Now, what would happen if we had a very extended object with lots and lots of charges in it? Well, that would be a material. That would be a macroscopic thing, like a cup or a piece of metal. And in order to think about what is going to happen to electric charges in that material when it's exposed to an external electric field, we need to first define two major classes of material. One of the classes is known as conductors. Conductors have electric charges in them that are free to move under the influence of an electric field. Let's call that E vector external. So imagine we have some blob of material and it's full of charges, and we expose it to an electric field, which I'll just draw here. It's a bunch of lines. In a conductor, many of the charges, electrons usually, are free to move about in the material as if they were unbound to any atom. And so what will happen is they will feel the electric field and they will respond accordingly. So if they're electrons, they will move against the lines of electric field. Conductors occur all over the place in nature. An excellent example of a conductor is copper. Copper is made of copper atoms. You thought about that a little bit in one of the homework assignments. And for all intents and purposes, at least for this course, the electrons in the outermost valence shell of each of those atoms are almost unbound to their parent atom. And so even a weak electric field will cause those electrons to move in response to the field. So, there are many common conductors that occur. Copper is one of them. Aluminum is a pretty good conductor. Okay, so those are very common household items that conduct electricity. Actually, the human body is a fairly good conductor too. It's not great, as we'll talk about a little bit more in the future, but you definitely feel electric shocks, and so clearly charges are free to move along the surface of your body. And when they leave your body, they excite your nerves and they cause pain. Now, there's another class of materials which is widely known as an insulator. And specifically, insulators have what are called dielectric properties. So what is an insulator? Well, in contrast with the conductor, charges are not free to move. So if we're thinking about atoms, say here we have a nucleus, and here we have a bunch of electrons orbiting that nucleus. The electrons are tightly bound. The parent atom greedily hangs onto them. And therefore, they can't respond to electric fields. Weak ones, and in many cases even strong electric fields, will not cause these electrons to respond. The atom hangs onto them very strongly. Now, a dielectric material is a material that possesses molecules with dipole moments. Now, either those dipole moments are intrinsic, much like they are in water molecules, for instance, or they are created by the application of an external electric field. But in either case, a dielectric is a material whose molecules possess an intrinsic dipole moment or can be induced to possess a dipole moment. Now, certainly if you keep applying electric fields to a material that is an insulator, eventually you will create such a strong field that even the parent atom won't be able to hang on to those electrons anymore, and you'll rip them free of their atoms. And at that point you have what is known as dielectric breakdown. Dielectric breakdown is a fancy way of saying that even strong insulators, under extreme conditions with high electric fields, can suddenly become conductors by ripping their electrons off of their atoms. Air is an excellent example of this. Now, during extreme conditions like those that exist in thunderstorms, you will get a large amount of electric charge that builds up on the ground and in the clouds. And when the electric field emitted by those charges becomes extremely large, about 30 million volts per meter. And we'll talk about what a volt is in a bit. But basically, when you have these large electric fields like those present in thunderstorms, you can suddenly cause dielectric breakdown in the air and you'll cause a spark to jump. And that spark will take the form of lightning. So air is an insulator. It, however, can be ripped apart by a strong enough electric field and forced to conduct. And that's quite dangerous. As you know, the sudden release of that energy in the form of moving electric charge can set things on fire, can blow out power lines, blow up transformers. It can do all kinds of damage. Again, thinking about common materials, we have copper conductor, insulators are common all over the place too. I mean, for instance, your average coffee mug is an insulator. It tends to keep the heat in, and it's also a terrible electrical conductor. Those properties are related to one another. Ceramic insulators occur all over the place. For instance, here's a common ceramic insulator that occurs near train tracks where the trains run on electric cables. A combination of an insulator and a conductor is present in every home, and that's a wire. So for instance, here we have a copper wire. Now, if you have a lot of electricity running through a copper wire, you don't want to be exposed to it. You could cause a very attractive path for the electrons to travel, and they might travel through your heart and kill you as a result. And so insulators can be placed around conductors to shield them so that you can't make physical contact with the conductor. And this is a very common arrangement, an insulator wrapped around a conductor to protect you from the conductor and to protect the conductor from you. Now let's think about what happens to something that conducts electricity in the presence of an external electric field. In that case, we have a situation where, for instance, maybe we have a blob here of material. And let's imagine that it's originally free from exposure to electric fields, and it's full of ions. We'll write those as little positive charges. Draw a bunch of these here. Okay. And originally, because this blob is exposed to no electric fields, the electrons that are weakly bound to the atoms are sort of uniformly distributed everywhere in the material. And the net effect of this is that when you add up all the positive charge from the ions and the negative charge from the weakly bound electrons, it sums to zero. So originally you have a situation where the electric charge is zero and this material is electrically neutral. Now what happens if you expose this thing to a strong electric field? In the case of a strong electric field, let's draw some electric field lines now passing through the material. You now have a situation where you have negative charges that are loosely bound to their parent atoms, electrons, and now you have an electric field that the material is being exposed to. Pause for a second and think about what's going to happen. If you want to pause the video, you're welcome to do that. But what's going to happen to the charges in this conductor in response to this electric field? Well, if the answer is they move, then you're absolutely correct. They're not going to just sit there and not do anything in response to the field. What's going to happen is that the electric charges are going to suddenly relocate inside of the material. So for instance, if I go ahead and cancel out my charges, if the electric field was pointing to the right, well, you can imagine that the positive charges are going to try to move as far to the right as they can get, and the negative charges are going to move as far to the left as they can get. Okay? And so let's put our electric field back here. So this is going to be the response of the material to the electric field, E vector. But let's take a look inside the conductor again. Now we have separated out the positive charge and the negative charge. This side of the conductor has a charge that's less than zero. and this side of the conductor has a charge that's greater than 0. Well, what's going to happen? You're going to get electric fields inside of the conductor. Let's draw those. Electric field lines originate on positive charges and go toward negative charges. So now you have an electric field set up inside the conductor in response to the external electric field, and all simply because electric charges are free to move in a conductor. So let's take a look at our picture again. We have this internal electric field. We'll call this E vector internal. But we also have an external electric field, E vector external. And we know that because of the principle of superposition, because electric fields are vectors, their magnitudes and directions will sum up to give you the total electric field inside of the conductor. You can't neglect the external electric field and what it's doing to this internal electric field. So we have a situation where the total is equal to the sum of E internal plus E external. Now, eventually, all of the charges are going to stop moving. They're going to get as far away from each other as they can, and they're going to get as far in the material as they can go in response to the electric field. And the net effect of all of this is something quite remarkable, and that is that this amorphous blob, which has electric fields inside of it, will suddenly cease to have a net electric field, because the sum of the internal and the external electric fields will cancel out inside the material. This is the definition of what happens when electric charges stop moving. Remember, electric charges move in response to an external electric field. But if they're not moving anymore, that means that their acceleration is 0. This is what's called electrostatic equilibrium. And basically what this means is that charges stop moving, or charges are no longer moving. When that happens, their acceleration is 0 on average, and that means that the electric field to which the charges must be exposed now must net out to 0. And again, that electric field is going to be the total electric field due to the internal and the external fields. And so what does the field look like now? Well, originally we had parallel lines of electric field going like this. They were originally passing through the conductor. Now they reach into the conductor, but they don't have any extent inside of it because they've been canceled out by the electric field inside of the conducting material. Conductors do not allow electric fields to occur inside of them. This is a fascinating result. Now, this is only true in electrostatic equilibrium. In electrostatic equilibrium, the acceleration is 0, so the total electric field inside of the material must be 0. If the charges are not moving, and I'm going to write this out, if charges stop moving, then the total electric field inside the conductor must be 0. If the charges stop moving, the total electric field is 0. If the charges are still moving, acceleration is not 0, and that must mean that there's an external electric field that's acting on them. Okay, so this is a very special case. In the next lecture, we will explore energy and electric fields.